Hello everyone, my name is Neha Kadam, and in this lecture we are going to learn about arithmetic circuits. This is the third part of this lecture, and let's see what we'll be covering. So we will be covering parallel ladders, subtractors, application, DIY, 4-bit adder, using adders for subtractions. So all these three topics we'll be covering in this lecture. So let's start with the parallel adding. So far what we have covered is the adding of 2-bit. So if you remember, in the adder and in the subtractor, we were adding just 2 bits, A and B. Whereas if you are asked to add multiple bits, then what you're going to do, what type of circuit you are going to create. So this slide basically talks about that, and in this one you can see that you have one half adder. This is your one half adder, and these are the two half adder used to add 3-bit numbers. So let me bring this up. So this is if you add A0 and B0, it means you are adding just 1 bit. And if you are adding A1, A0, B1, B0, then you are adding 2 bits. And if you are adding A2, A1, A0, adding with B2, B1, B0, then this means you are adding 3 bits. Okay. So in this one, if you have to, so far the circuit which we saw previously in the last lecture for the adder, we saw that how we were adding the 2 bits using the half adder and the full adder. Now we are going to add 3 bits. Okay, so when you have to add 3 bits, you'll be using one half adder and 2 full adders. So if you see, this is the half adder. A and B, A0, B0 is basically going into this adder, and this is the sum, and this carry out will go into the another adder and will work as a carry in. So the carry output of this adder will be your carry in for the second adder, and this adder, if you see, is a full adder. If you remember, then in the full adder we had A and B input, and then you had a carry in, and you had a carry out, and then you had a sum. So that's what is happening, and whatever the sum is, sum comes out, basically goes here, and then the carry out goes into the another your full adder and work as a carry in, and then you have these two inputs going in here, and then sum is here, and then this carry out, the final carry out basically works as the most significant bit. So this is your most significant bit or most significant digit, and this is your least significant digit or least significant bit. So if you notice, the least significant digit is the sum from the half adder, and the most significant bit is basically the carry out from the final adder, final full adder. Now, so we want to add this. If you make this circuit, then you can add 3 bits, and you can further basically make the logic diagram. You remember we used XOR gate and AND gate to make the half adder, and to make the full adder we used 2 half adders. So that kind of circuit you can use if you are interested to make the circuitry of this logic circuit. So this is your this is how you do the parallel adding. Now let's see next. So this is a 4-bit parallel adder. So you're going to add the 4 bits using 4 full adders. This is your 4 full adders which has been shown over here, and then you have output generated over here, and these are the input bits which you will add. So we will see. Let's move on to next. Enter binary numbers to be added here. So from here you will send the binary inputs. If you look closely, that all the A's, these 4 represents your A input, and these 4 represents your B input. So let's say if you are asked to add 0011 plus 1000, then your output is going to be 110 1, and this will be 0. That is your carry out. And this basically the lower significant bit in this particular case basically represents your sum from the first adder, and then the most significant bit is basically represents your carry out. So this is your carry out, and in this you will have to fetch some carry in into the circuit, because in this one we are using all full adders. This is not like we are using half adder here and rest of them are full adder. So if you are using all full adder, if you are making the parallel adder using all full adders, then you'll have to assume some carry in going into the circuit. So right now it's saying that low carry in is going into the full adder. So let's see a few more examples. So in this example, we are adding 1100 to 1111, and if you do the computation, if you add these two binary numbers, you will get this answer. So the answer should be 11, and then 0, because you have 1 here and 1 here. If you add them up, then you will have some 0 and then borrow, and then carry will be 1. So that's why you have 0 here and then 1 carry here, and then 1 plus 1 is again you will have 2, which means 1 0, and then carry will go to the other step, and then the previous carry will basically add in up here. So that's why you have 1 here and then 1 here. So this is going to be the result, and again this is going to be your least significant bit, this is going to be your most significant bit. Now let's see another example. In this one we are adding 1110 plus 0110, and if you add them up, then you will have 10100. So this type of adder you see here, they can be available in the IC form, and you can use them in the laboratory to construct different experiments. You can make the calculator also using those ICs. So it says the same thing. Parallel adders are available in the IC forms, and then now we are going to see an application of 4-bit adder. So this is 7483 4-bit binary full adder, and it has 4 inputs. All it's starting from A0 to A3, and then another input which is starting from B0 to B3. So these are your inputs, and then you have carry input tied to the low, which is 0, and then you have all these are the sums, your outputs, and then this carry out is basically your most significant bit. So this IC which you see here is similar to the circuit which we saw in the previous slide. So this type of IC you can use to make your make any circuit, and you can make this this full adder in the laboratory, because now you know the circuit of the full adder, so you can easily make this circuit. So carry input to 7483 IC, pin 13 is grounded, makes 7483 IC a 4-bit adder. And then you have so problem 1, if you add these two, then what is going to be the output? So you are going to get 1 1 and 1, and then you will have 2 zeros. So 0 0 1 1 1. If you add these two numbers here, where 1101 is basically represents your all the B's starting from B0 to B3, and then these represents your all A's, A0, so like A0, A1, A2 and A3. Okay, and when you add them up, you will get you should get 10100. So that's the answer. And let's do this problem when you are asked to add all 4 ones. So 1111 plus 1001. So this is your A and this is your B input. So the output for this particular case, if you can take a pause and see like what answer comes out, and then you can match with my answer. So my answer for this binary addition for 4-bit number is 11000. And then for this one, it is 0011 plus 1011. If you add them up, then you will get 01110. And then 1111 plus 1111. So this is your A, this is your B, and if you add them up, so 1 plus 1 is your sum is going to be 0, and then carry is going to be 1, which is goes here, and then 1 plus 1 and then the carry, that will make your output the sum as 1, and then so on. So your answer will come out to be this 11110. So this is something you can do. Now let's see next. So you can try this DIY adder circuit in the lab and test it out for different combination of inputs and see, check it out if your answer is matching with your theoretical answer. Now next is the quiz, and so this is interesting, and in this it says with the top full adders C in input low, this operates as a half adder while the bottom three are full adder. So is it true or false? It is true. So if you look closely, this above full adder, this is actually a full adder, but if you tied up this C in carry in input to the low, then this will act as a half adder. And I think I forget to mention in the previous slide, like if you add this C in to the low, then this first adder will be your will work as a half adder. Okay, so yeah, so this statement you see here is true, so the answer is going to be true. And then you have when the 4-bit parallel adder adds binary 1100 and 0011, then the sum appearing at the lower right will be. So you have to like add these two numbers 1100 and 0011. If you add them up, then your answer is going to be 1111. But then don't forget this because these are the four inputs. You got it here, but then you have a carry and you don't have a carry in this case, so your carry is going to be 0. So your answer is 01111. When the 4-bit parallel adder adds binary 0111 and 1001, what will be the output? So in this case, you have, so if you add 1 plus 1 is going to be some 0 and 1 carry going in here, and then again 1 plus 1 is going to be 0 sum and then carry. So if you do the computation, then it should come out to be your carry will be 1 in this case, and all these fours will be 0. So that's what you got here. Your carry is 1 and all these fours are zeros. Now adding 1101 and 1001. So if you add this up, then you should get, so pause the video I would say at this point and then do the calculation and match it out if your answer is correct. So for this, the answer is 10110, and then another one 0011, 0110. So let me take an example of this one using this highlighter pen. So you have 0 0 1 1 and then 0 1 1 and 0. So you want to add these. So let's make the addition sign here. So 1 plus 0 is going to be your 1, and then 1 plus 1 is going to be some your 0, and then carry will go in here. So let's make like this. This is our carry. So 1 plus 1 is going to be your 0, and then again carry, which will go over here. So you're going to get 1001, but notice that we have a carry out. In this case, we do not have any carry, so we will put here 0, and that's what your answer is going to be. Let's see. This is your 01001. All right. I will quickly take an example for this one. This was the interesting case. So let's do it here. 1 1 0 1, and then 1 0 0 1. So we have to add these two numbers. So 1 plus 1 is 0, and then carry is going to be 1. So okay, so 1, so this is going to be 1 here, and then this 1 here, and then this is 0, and this 1 here. So you will have 1 0 1 1 0. Let's see if our answer is correct. Okay, so you see here 1 0 1 1 0. Now let's do one more. For this one, this is an interesting one. Pen. Okay, so 0 1 1 1, and then 1 0 0 1. Adding these two numbers, so 1 plus 1 is 0, and then carry is 1, and then 0 plus 1 is 1, and adding with the carry, it's going to be your 0 here, and then 1 here, and then 0 plus 1 is 1, and 1 plus 1 carry is going to be 0, and then 0 and 1 is going to be your carry, because 1 plus 1 is 2, and in binary it is 1 0. So 0 here, 1 here, and then 1 plus 0 is 1, 1 plus 1 is going to be 0 here, and then a carry, and this carry will basically come out here. So that's why you have 1 0 0 0 0, and this is your answer for this problem when you have 0 1 1 1 added to the 1 0 0 1. So that's how you do the addition in binary. So I'll just quickly move on to so this we already did, and then you have this example adding all these fours. If you add them up, you will get 1 1 1 1 0. And then same with this 1 0 1 0, adding with 1 0 0 1 will make up your 1 0 0 1 1. So this was your 4-bit parallel ladder, and now let's see the parallel subtractor using full adders. So this is an interesting circuit. The reason why, because we are trying to create the parallel subtractor using full adders instead of full subtractor. We are using full adders. You can create the parallel subtractor using 1/2 a subtractor here, and then 4 full subtractor. But then in this particular circuit, we are using adders to create the subtractor. Now the logic is how to create the logic for making the parallel subtractor. So the logic is you do the 2's complement in order to basically subtract the 2 digits, this 2 inputs. So to provide the 2's complement, you will give the 1's complement through these inverters. You see these inverters or the NOT logic. Through this you provide the 1's complement, and another complement you provide through this carry in. So this carry in is tied to high logic, which is 1, and through this carry in you will provide the 2's complement. I know at this point of time it would be difficult to understand what is 2's complement. This is we are going to see in the next lecture, but for now just understand when you want to subtract in a parallel subtractor using full adders, you will have to give the 2's complement. So we can say that the number to be subtracted is your B is first have to pass through the inverters to obtain its 1's complement. So you get the 1's complement here, and the 4-bit adder then adds A, then the 4-bit adder your adds this A and 2's complement of B to produce the subtraction. And here you see these are the outputs which represents the result of the binary subtraction, A minus B, and then you have a carry out. You see here is your carry out, and this carry out represents the polarity of the result. So if your A is greater than B, your A input is greater than B, then your carry out is going to be 0. Whereas if your A is smaller than B, then you will have some carry out, and that will be equals to 1. And the result in this case is going to be in the 2's complement. Now let's see inverters. These are the inverters, and high add carry in input makes this perform as a full adder circuit. Binary numbers to be added subtracted are input here, so and then the result comes out here. High add carry in input acts like adding +1 to a 1's complement number to form the 2's complement. 1's complement is formed by 4 inverters. So we already discussed that 1's complement is given through this, and the 2's complement given through the C in. When you add 1, that will create your 2's complement. Now let's see if you subtract these two numbers, then you will get this output here. And let's see next, if you subtract these two numbers, then you will get this output here. So what you can do, you can basically put this number here and see what your original number was here, and all those number will be complemented here, and then your 1 will be added to give it a 2's complement. And then this and then they are basically they basically form the subtraction, and if you have these two numbers, then your output will be this. Now this is the end of the lecture. I would advise you to watch the lecture after this, which basically tells you about the 2's complement, and once you see that lecture, you can come back to this topic again, and then you can check it out, like how the circuit is working, because at this point you do not know what is the 2's complement. So you can come back again to this topic after watching the 2's complement lecture, and then put up different values here and see that how this circuit is working. You can also create the truth table for this particular circuit and to observe like what will happen to the output to the output for different combinations of inputs. So this is the end of the lecture. Thank you so much for watching.